Hello and welcome everybody to today's lesson about protection in electrical power systems. Today I suggest to focus on transformer vector groups. So these transformer vector groups are motivated by the fact that earth faults on one side of the system, in this case on the right side, which change the voltage from regular voltage into elevated voltages on the secondary side, should not be transferred to the primary side. And this is done by this vector group and vector arrangement of the transformer windings, which in this case is delta Y. So if you have a delta Y transformer, the primary side voltage is not disturbed, not afflicted by this fault, and we have healthy and regular phase to ground voltage. And this is the reason why we have transformer with different and adjusted vector groups. Now we start with a very basic model which is quite well known. This is the basic model of a single phase transformer where the two windings have equal turns. So that means voltage U1 is applied, comes out is voltage U2 on the other side, and the currents are the same. And now I open this, I just redraw that, and then it can be seen that this transformer, the bottom one, has in its functionality exactly the same as is the upper one. Now let's apply this to a three-phase transformer model, which later on will be called YN0. So the three-phase model is a triplification of the single-phase model which we had before. You see, it has moved up, but now we have three phases. Phase 1, 2 and 3. And in all these phases we have currents and we have voltages. So now let's focus on the current. The current on the low voltage side is, in case of regular loading, a perfect star. This is transferred to the primary side just again as a perfect star. Now, if this is a ohmic load, which I assume for the simplification of phase angle considerations, the voltages are more or less the same. So we have the same voltage, perfect voltage on the primary side. We can check the same as well if we first turn the currents on the low voltage side into their voltages and we transform these voltages. So this is the same voltage appearing on both sides of this transformer. And this is why it is called YN, that means Y on the primary side, and it has a neutral, and YN on the secondary side, and there is no phase shift, so this is meant as 0. Now, the next complication is the three-phase transformer model type DYN something. D is for delta, N is for star. And now let's see how is this coming. This again is the star-star transformer, the YY transformer. But now watch what happens in case of a delta transformer to the primary windings. The primary windings are connected in this Z form, and let's see what happens to those currents. So let's start again in phase number 1 with a current on the low voltage side. So the low voltage current is transformed, if the number of terms is equal, to the same current on the primary side. So the same happened as it is in phase A, happens in phase B and in phase C. And now let's see what is the phase C current going to. So it comes out of this third winding, goes up to the left, and here the two currents merge and they eventually make up the real primary current. And now let's see what does that mean in terms of phasors. So we have the phasor of the low voltage side. Let's concentrate on the blue one, which is phase 1 or phase A here. This is transferred as before, identically to the primary side. Now we have this equation that the sum of the real high voltage side input current and the current IC makes up for the blue current, and this can be rewritten, and now the phasors act accordingly. So we obtain a high voltage primary current I sub A1 in violet, and you see it is turned. Now let's concentrate on this. Since it has increased in size, we resize the primary number of windings, so we multiply them by a factor of √3, so the current is divided by √3, and now this is the same size of the current, the same amplitude on the primary side. Now we make a little graphical intervention by turning these two stars 30 degrees counterclockwise. So this means the current on the primary side is upright and the current on the low voltage side is preceding it by 30 degrees. The same happens to the voltages, and this is the reason why we give this type of transformer the vector group 11. Why it is 11? The primary side is 12 and the secondary side is on 11 o'clock. That means 30 degrees counterclockwise. Now the next one is the most usual one, that is dyn5. So again we have the previous one, and now we shift the polarization of the secondary winding in the opposite direction. You see, it was before, now we have changed this and see what happens to the currents. The currents on the secondary side are turned by 180 degrees, and now we repeat the same procedure as before. We focus on current phase 1 as well as on voltage of phase 1, and we see that now these are turned into the again upright phases on the primary side. And when it comes to this dial expression, we see that we have now 12 o'clock on the primary side, 5 o'clock on the secondary side, and this is why this transformer group is called dyn5. So this was today's lecture about transformer and their vector groups.